Hello friends, I welcome you in lecture number 10 on partial differential equations of first order. We were discussing Lagrange method for solving Quasilinear partial differential equations. In last lecture we have introduced type number 4 of solving Lagrange Quasilinear equations. So as we have discussed, in type 4 type of problems we are generating new fractions such that the numerator is differential of the denominator, and we try to compare those new generated fractions to find out the solutions of auxiliary equations. So in this lecture also we are going to do some more examples on type number 4 of solving Lagrange auxiliary equations. So we start with example number 1. We have given Lagrange auxiliary Lagrange Quasilinear equation. So as we know, the method starts with Lagrange auxiliary equations. So Lagrange auxiliary equations are dx divided by coefficient of small p, which is x square minus y square minus z square, dy divided by coefficient of small q, which is 2xy, and dz divided by the term on right hand side, which is 2 into x into z. So first we try to check whether it is possible to compare these three ratios or fractions. So we can observe fractions 2 and 3. Here differentials are dy and dz, and there is x in the multiplication here. So we can see if we compare these last two ratios, then we will be able to cancel out 2x, and everything will remain in terms of y and z. So here it is possible to find out one solution by taking last two fractions. So we write that taking last two fractions of 1, we have dy divided by 2xy equal to dz divided by 2xz. So we can cancel out 1 by 2x, and we have dy upon y equal to dz upon z. So this is separable ordinary differential equation. So we can find its solution by direct integration. So integrating, we obtain log y equal to log z plus arbitrary constant we write as log c1, and this we can rewrite as log y minus log z equal to log c1, and using property of logarithmic function, this we can rewrite as ln y by z, which is equal to ln c1, and because logarithmic function is 1 function, this implies y by z equal to c1. So therefore the first integral of Lagrange auxiliary equations is u equal to y by z. Now to find out second integral, we try to check whether it is possible to compare any other two fractions, but it is not possible here. If we compare first two fractions, then we have dx and dy is in first two fractions, differentials are dx and dy, so z must be absent, but here we have negative of z square, which is not possible to cancel out. Similarly, if we try to compare last and first fraction dx and dz, then y must be absent, but here we can see it is not possible to cancel out this y. So it is not possible to find out this second solution by directly comparing the fractions. So we have to select appropriate multipliers and we have to generate new fraction such that numerator is exact differential of the denominator. So here we can see we have x square, y square, z square here, and if we select multipliers x, y, z, then we may have the fraction such that numerator will be exact differential of the denominator. So I select x, y, z as multipliers. Each fraction of 1 equal to so I write here numerator will be dx is multiplied with x, dy is multiplied with y, and dz is multiplied with z. And here we have to multiply x with x square minus y square minus z square. So that I write here x into x square minus y square minus z square plus y into 2xy and z into 2xz. So y into 2xy plus z into 2xz. So numerator remains as it is, x dx plus y dy plus z dz, and here we simplify. This is x cube minus xy square minus xz square. This is 2x into y square plus 2x into z square. So again we can rewrite this as x dx plus y dy plus z dz x cube. Now we have minus xy square and this is 2xy square, so that will be x into y square. Similarly we have minus xz square plus 2xz square, so that is x into z square, and there is a x in each term, so we can take x common and we are left with x dx plus y dy plus z dz, and here we have x common, x square plus y square plus z square. So this is our new fraction. Now we try to compare this new fraction 2 with any one fraction in equation 3, in equation 1. So here we cannot compare with first fraction dx upon x square minus y square minus z square, but here we have x here, so it is possible to compare with fractions 2 or 3 because x will cancel out. If we compare with second fraction, we will have dy upon y and x will cancel out, and similarly if we compare with last fraction, x will cancel out and we will have dz upon z. So we can compare either with second fraction or last fraction. So suppose we compare with last fraction. So we compare the new fraction 2 with last fraction of equation 1. So taking fraction 2 with last fraction of equation 1, we get last fraction of equation 1 is dz upon 2xz, and that we compare with this fraction number 2, x dx plus y dy plus z dz plus z dz divided by x into x square plus y square plus z square. So we can see x will cancel out and we transfer this to on right hand side. So we have dz upon z equal to 2x dx plus 2y dy plus 2z dz divided by x square plus y square plus z square. So if you observe right hand side, this 2x dx plus 2y dy plus 2z dz is nothing but exact differential of x square plus y square plus z square. So therefore we can rewrite this as x square plus y square plus z square, and here differential of x square plus y square plus z square. So this is also separable. So if we integrate on both sides, the left hand side is integral of 1 by z with respect to z is log z, and here integral of derivative of x square plus y square plus z square divided by x square plus y square plus z square is log of x square plus y square plus z square plus constant of integration, which we adjust as log c2 because there is a log in remaining terms. So therefore log z equal to log of c2 into x square plus y square plus z square, and because log is 1 function, we have z equal to c2 into x square plus y square plus z square. Therefore z divided by x square plus y square plus z square is nothing but c2. So therefore the second integral of Lagrange auxiliary equations is v equal to z divided by x square plus y square plus z square. So therefore the general solution of given equation is arbitrary function of uv equal to 0, and we have find out what is small u. It is u equal to y by z. So we put values of u and v. So u is y upon z and v is z divided by x square plus y square plus z square equal to 0. So where phi is an arbitrary function. So this is the general integral of given Lagrange Quasilinear equation. So here we have find out the solution first by directly comparing last two fractions of equation 1, and then we have generated one new fraction such that we can compare it with second fraction or third fraction of Lagrange auxiliary equations. Next example, given equation is Lagrange Quasilinear equations. So we start by writing Lagrange auxiliary equations are coefficient of small p is 1, coefficient of small q is also 1, and right hand side is x plus y plus z. So you can observe it is possible to compare first two fractions. So taking first two fractions of 1, we have dx equal to dy, which is separable. So integrating, we obtain x equal to y plus c1, that is x minus y equal to c1. So therefore the first integral of Lagrange auxiliary equations is u equal to x minus y. Now to find out second integral, we have to select appropriate multipliers. So here I consider 1, 1, 1 as multipliers and I generate new fraction. So taking 1, 1, 1 as multipliers, each fraction of 1 equal to, so we have dx plus dy plus dz, and in the denominator 1 plus 1 plus x plus y plus z. We just simply have to add. So 1 plus 1 plus x plus y plus z. So this is nothing but 2 plus x plus y plus z. And if you can observe, we can write this numerator as differential of 2 plus x plus y plus z, because differential of 2 is 0 and differential of x is dx plus dy plus dz. So this is new generated fraction in which numerator is exact differential of the denominator. Now this new fraction 2 we can compare either with first fraction or second fraction. We cannot compare with last fraction. So suppose we compare with first fraction. So taking first fraction of 1 with fraction 2, we get first fraction of 1 is dx and the fraction generated is differential of 2 plus x plus y plus z divided by 2 plus x plus y plus z. So this is separable, and integrating we obtain small x equal to log of 2 plus x plus y plus z divided by log of c2. So therefore small x equal to log of c2 into 2 plus x plus y plus z using property of logarithm. So this is the solution of Lagrange auxiliary equations, second solution. And if we write down the final solution, therefore we have to write this as, okay, but we cannot, we have to write this as some function of x, y, z equal to constant. So if we use the property of logarithmic function, that if log y equal to x, then y equal to e raised to x, or if we go in reverse way, if we take log on both sides of this, we have log y equal to ln e raised to x. So we know that exponential and logarithmic function are reverse of each other. So from this I obtain c2 into 2 plus x plus y plus z equal to e raised to x. So therefore we have e raised to x divided by 2 plus x plus y plus z equal to C2. So therefore we can take V equal to e raised to x divided by 2 plus x plus y plus z. So this is the second integral of given Lagrange auxiliary equations. So therefore the final general solution is, therefore the general solution of given equation is arbitrary function of uv equal to 0. That is, therefore phi of u is x minus y. And v is e raised to x divided by 2 plus x plus y plus z. Equal to 0, where phi is an arbitrary function. So in this way we can decide the solutions of Lagrange auxiliary equations, and we are able to write down the general solution of given Lagrange quasi-linear equation. We take one more example of type 4. So last example of type 4, find general integral of this equation. Another name for solution is integral. So sometimes they can ask you find general integral of given equation. So either integral or solution, both are the same thing. So as usual we start with Lagrange auxiliary equations are dx divided by coefficient of small p, which is x into z, dy coefficient of small q, which is y into z, dz divided by right hand side. So we give this number 1. Now if we observe first and second, it is possible to compare first and second fractions, because we are able to cancel out this z and remaining terms will be in terms of x and y. Let us try for second and third fractions. We have dy and dz, so x must be absent, but here x is not possible to cancel out. And if we compare dx and dz, then y must be absent, so which is also not possible to cancel out. So the one solution can be obtained by comparing first two fractions. For second solutions we have to think for another fraction generation. So taking first two fractions of 1, we have dx divided by x into z equal to dy divided by y into z. So it is possible to cancel out z here, it is in the product. So therefore dx upon x equal to dy upon y, which is separable. So if we integrate, we obtain log x equal to log y plus log c1, and this I can rewrite as log of y into c1. And because log is 1 function, we obtain x equal to y into c1, or x divided by y equal to c1. So therefore the first integral is u equal to x divided by y. Now what about second integral or second solution of Lagrange auxiliary equations? So here we will select multipliers 1 by x and 1 by y and 0. So if I multiply this 1 by x, x will cancel out, I will have z, and here if I select 1 by y as multiplier, y will cancel out and I will have z. So that z will be combined with this and we will obtain 2z, and then we will try to compare that new fraction with any of these three fractions. So the multipliers which we will select are 1 by x, 1 by y, 0 as multipliers. Each fraction of 1 equal to 1 by x is multiplied with dx, dy is multiplied with 1 by y, and dz is multiplied with 0, so that part is 0. And here 1 by x into xz and 1 by y into yz into and 0. So 1 by x into xz plus 1 by y into yz plus 0 into denominator of last fraction xy. So xz into yz. Xz is multiplied with 1 by x, yz is multiplied with 1 by y. So this is going to be, now this I can write as y dx plus x dy, and in the division I have x into y, and this is going to be z plus z, which is 2z. So finally the new generated fraction is y dx plus x dy divided by, this is 2z into xy, that is 2xy into z. So this is the new fraction, and we will try to compare this new fraction with any of these three fractions. So we have auxiliary equations are this one. So suppose I compare with last fraction, then I have x into y in the denominator, and here I have z. So x into y will cancel out and z will be multiplied with dz. So it is better to compare with last fraction of 1. We cannot compare with second fraction, because if we consider dy upon yz, then yz will cancel out and we will have x, but differential is dy, so it is not possible to compare with second fraction. Similarly, there will be same problem with comparing with first fraction. So we compare with last fraction of equation 1. So taking fraction 2 with last fraction of equation 1, taking fraction 2 with last fraction of 1, we have fraction 2 is y dx plus x dy, and here 2xy z, and last fraction of 1 is dz upon xy. So this is dz divided by xy. So we can see xy will cancel out, and this 2z we consider with dz, and y dx plus x dy is nothing but exact differential of x into y. So d of x into y equal to 2z dz, and this is separable. So integrating we obtain integral of d of xy is x into y. This is 2 into z square by 2, that is z square plus c2. Therefore x into y minus z square equal to c2. Therefore second solution of Lagrange auxiliary equations is v equal to xy minus z square, and therefore the general integral is arbitrary function of uv equal to 0. Therefore now we find out what is our u. So u is x by y. So we put u equal to x by y, v is x into y minus z square equal to 0, and where phi is an arbitrary function. So we stop here. This is the last type of Lagrange quasi-linear equations. So as we have discussed in first order partial differential equations, we are going to discuss this topic, first order partial differential equations, into two subtypes. First one we have just finished, Lagrange quasi-linear partial differential equation and its solutions. How to solve Lagrange quasi-linear partial differential equations. Another classification is non-linear partial differential equations. So our next lecture is now on non-linear partial differential equations. So here we are going to discuss, again we are going to divide this into two categories. First we will discuss J.Prajapati's method of solving non-linear partial differential equations. Then we will discuss some standard forms of non-linear partial differential equations. So if you are watching this channel first time, kindly subscribe this channel for upcoming lectures, and we are going to upload lectures of each mathematics subject of engineering. So I hope you like this lecture series on engineering mathematics. Please subscribe it if you have not subscribed for upcoming lectures. Thank you.